Hi, and welcome to D1.4 Accelerated Systems. Again, there isn't really anything new. There's not a lot of new content to talk about, but there's just so much more complicated examples that we're going to go through. First of all, we should probably mention what accelerated systems are. So accelerated systems is a system of objects that are being accelerated together. So usually you've got two objects that are either tied together kind of left and right, like so, on a surface, and you can pull them along like that. Or you could have maybe two objects hanging and they'd either be being pulled up or let down. You could also have the third option, I suppose, is you could have two objects that are sort of pushing up against each other. And if you pushed on, say, this bigger one on the left and push it to the right, it would run into the smaller one and they would move along as a system too. So those are kind of the three main types of accelerated systems that we'll look at in this chapter. But accelerated systems just kind of means more than one object, a system, and then that they're being accelerated. So let's take a look at example one. Example one, a dog team is pulling a train of two sleds. Sled number one is 23 kilograms and tied to the dog team. Sled number two is 56 kilograms and tied to sled number one. If the dog team pulls the sled with an 867 Newton force, what is the magnitude of the force that pulls sled number two? So there's a lot of information given these questions because they're a bit more of a system. So I highly recommend, it's not even a recommendation at this point, you need to start drawing pictures. So I'm going to actually draw two for this one. I'm going to try and figure out what's going on in my head. We've got two sleds that are kind of trained together, and I'm just going to draw them as squares, and then they're tied to our dog team. So sled number one is 23 kilograms and tied to the dog team, and sled number two is 56 kilograms and tied to sled number one. So this is sled number one out in front, this is sled number two, and behind sled number one, and this is the dog team. If the dog team pulls the sled with an 867 Newton force. Okay, so now we're going to have to talk about forces. And I'm actually going to redraw this diagram. I've got a bunch of extra things in this diagram, so it'll get in the way of me drawing an appropriate free body diagram. So here now is my sled number two, and here now is my sled number one. And I'm going to get my red pen out to draw my forces. It says the dog team pulls this first sled with an 867 Newton force, and I'm just going to write that as an FA, and I can write equals 867 newtons right here. And it turns out then that our system doesn't include the dog team. All we have for our system is these two objects that are being pulled. Our dog team just helps us imagine what type of system this is in reality. I'm going to go ahead and I'm going to add my easy forces. I've got an FG going down here. I've got an FN going up on sled number one. I've got an FG going down on number two, and also an FN going up on number two. And you'll notice now we're going to run into some issues. Neither of these sleds have the same masses, but we have two FGs and two FNs. So in our head, that'll get confusing if we start doing algebra using all of these variables. So I'm going to add a second little number to these subscripts so that I now have an FG1, which acts on box 1, FG2 acts on box 2, and I'm going to do the exact same thing with my normal forces, FN1 and FN2, and now each force has a unique subscript so that I can tell what they are if I have to do algebra on them. So this, I think we've done all of the easy forces, and now we've got to think about some of the more complicated forces. What you want to imagine is that if you have you should be able to independently cover up one of these, and it should act on its own. So right now, if I look at sled number two, I can really easily see that it should not be moving left or right. And I want to kind of think about it. Okay, well, what's making sled two moving to the right? Is it staying in the snow while sled one gets pulled away from it? No, there is a rope attached to it that's going to be pulling it forward. So I'm going to draw that force, and I'm going to call it an Ft right there. And so if I have a force of tension pulling on box 2, I want to think about that. What would happen on box 1? Well, Newton's, I believe it's third law, says every action has an equal and opposite reaction. So that means there's going to be an Ft on box 1 as well. Some people don't like this. They get a little bit confused and they say, well, why? That doesn't make any sense. What about Fa? And Fa, yeah, there would be an equal and opposite force on that dog team as well, pulling it backwards of 860 newtons. But again, we're not counting this dog team as part of this system. We don't even know the mass of the dog team. We don't know what force acts on the dog team. We just know that the dog team is pulling the sleds with an 867 Newton force. So we're not going to think about the dog team right now. The other thing I would like to point out is the relationship between Ft1 and Ft2. Ft1 and Ft2 are equal and opposite action-reaction pairs, which means they are exactly equal and exactly opposite, which means I'm actually going to get rid of this subscript 2 and this subscript 1. Why? Because they are exactly the same. So when I look at this now, I have a bunch of different options for Newton's second law, which is usually where we go after we draw a free body diagram, which I'm kind of scribbling down in this corner here, except I forgot an equal sign. The net force is equal to mass times acceleration. So we know already that we can look in the x-plane and the y-plane. What I'm going to do really quickly is I'm going to look at the y-plane in this corner over here, just so that we can get it out of the way. It's going to turn out to be not the most useful step, but I want to go through it so that we don't have to think about it anymore. So in order to do this, in the y-plane, we also have to choose a box to look at. Am I going to look at box 1 or box 2? Well, notice how they're both pretty much the same. Neither are being accelerated up or down. They're both kind of sitting on this flat surface, which means that if I call, let's call up and right positive, up. Uh-oh, my pen chose now to die. Up, oh, came back to life, and right, positive. That would mean that Fn2 minus Fg2 would be equal to ma. My acceleration up and down, as we just talked about, is 0, so that cancels out, and we find that Fn2 is equal to Fg2, that they are equal and opposite. And that's the balanced force on box 2. And we'll notice that box 1 is exactly the same. That might help us in the future, but it doesn't really help us right now about trying to find the magnitude of the force that pulls box number 2. And we'll notice how that this is then the force we're looking for, Ft2. So, one of my options to apply Newton's law, and right now, well, let's do it. I'd be like, I'm looking for Ft. If I'm in Physics 11, I'm looking for Ft. I'm going to write the sum of my forces. Maybe I do this in a different color. I'll do it in blue. The sum of my forces on box 2 is equal to the mass of box 2 times its acceleration. Notice how I didn't stick a subscript on my acceleration, and that's because since my sleds are tied together, they're going to accelerate at the same rate. So the acceleration of box 1 is going to be the same as the acceleration as box 2. So Ft2 is equal to m2a. I've already called to the right positive, so I've just got an Ft, and that's equal to m2a. And if I wanted to, I could put a little x down there too, an F2 in the x-plane. I'm just looking at my left and right forces. So if I look at this, I'll notice that I don't know what F force of tension is, because that's what the question is asking, and I don't know what the acceleration is. So I have two unknowns in this equation, and I'm essentially stuck. I haven't done anything wrong, so I'm not going to erase it in case this becomes useful to me in the future. But my other option is to look at, maybe I'll do this one in green, the sum of my forces on box 1 in the x-plane is equal to the mass of box 1 times its acceleration. I have decided to the right is positive, so I've got an applied force minus that same force of tension is equal to m1a. You'll notice here that I have a little bit more information. These equations aren't exactly the same. This one has an FA in it, and I know what FA is, so I get a little bit excited. I was like, oh, I got one more thing that I know, but I still don't know what FT is, and I still don't know what my acceleration is, so I'm stuck here. And I can't solve for anything. And again, I haven't done anything wrong, so I'm just going to leave it. But I now have to explore my third option, which I'm going to do in purple here. And the third option I can do is I can look at the sum of the forces on this whole system is going to be equal to my mass of my system times the acceleration. This is where people get cheeky and try to take shortcuts. If you're looking at the sum of the forces on the system in my x-plane, you need to look at all of the forces in the system in the x-plane. And you can't jump the gun here. I have 1, 2, 3 forces in my x-plane. My FA is positive. This first FT is negative. This second FT is positive. And that's going to be equal to my mass of my system, which is m1 plus m2, and that's equal to the acceleration. So at first glance, I'll be like, well, I have the exact same problem. I still have the force of tension, and I still have my acceleration. I have two unknowns. I can't do anything. However, you'll notice that one of your FTs is positive and one of your FTs is negative. So if I combine my like terms, that's equal to 0, and I'm left with my applied force is equal to m1 plus m2 times my acceleration. So now this isn't what the question has asked me to find, but it's something that I can find, and at this point in time I'm a little bit lost, so I'm just going to keep going down this path and solve for, I know what FA is, I know what my mass is, I know what my second mass is, I can solve for my acceleration. My acceleration is equal to FA over m1 plus m2, so my acceleration is equal to 867 divided by 23 plus 56. I think somewhere here I might even have my acceleration. I'm plugged in already. Let's see what happens if I grab this guy and pull him down. And I believe that my acceleration is 10.9746. So again, I'm not going to round it to 3 sig figs because it's not a final answer. I'm going to put my ellipses there so that I know that I'm using all of those decimals. So now that I've found my acceleration, what I could do is I could go back and I could look at this first equation that I wrote down. And I noticed that now I have one of my unknowns. And I only had 2 unknowns, so now I know what to do. I can go back to my blue, and I know that T is going to be equal to m2, which is 56 kilograms, times my acceleration, which is 10.9746, dot, dot, dot. And I find that my force of tension now is, which I've written down up here, $252.417 newtons. For some reason, I feel like that answer is wrong, so I'm going to double check that and plug it into my calculator. I've got a 10.9746 times 56, and I get 614. $614.5776. My FT is equal to 615 newtons. I'm just going to look back. Sled number 2 is tied to the dog team. Yeah. Sled number 1 is tied to the dog team. Sled number 2 is tied behind it. That's a 615, 867. All this is making sense to me. I'm liking it. Quick double check. quick sanity check finds that that looks like it's right. You'll notice that I could have taken this acceleration as well, and I could have plugged it into the equation of number 1. I could have taken this, I could have substituted in here, and the only reason I didn't is because it's subtly more complex. But you would get, or should get, the exact same answer. And we should probably try that. So I'm going to go to green, and I'm going to go solve for my force of tension. My force of tension here would be equal to Fa minus M1A. My Ft is going to be equal to my applied force, which is 867, minus M1, which is 23, times my acceleration, which is the 10.9 stuff. And if I plug that into my calculator, and this is also a reasonable thing to do if you want to double check that your answer is right, I also get Ft is equal to 615 newtons. So this, I would argue, is the physics way of doing it. You have three things to look at in a system. You can look at option 1, or I should call this option 1 because it's box 1. You can look at box 2 in isolation, or you can look at the whole system by itself. There's also a bit of a mathy way you can do this. If you've been doing your math recently, you know that if you have two linear equations and two unknowns, this is completely solvable just using math. So what I'm going to do is I'm going to take these two blue equations. I've got my Ft is equal to M2A, and I also have my Fa minus Ft is equal to M1A, and then if you remember from Math 10, you can solve by addition. So I can add the left-hand sides together, and I can add the right-hand sides together. And if I do that, what I get is I've got my Fa, I've got a positive Ft and a negative Ft, so that's a 0. And I've got an M1A plus M2A. If I factor the M1 and M2 out, I get an M1 plus M2 times A, and you'll notice how that is exactly the same as what I ended up in the purple up there. So they are two different ways of doing the exact same thing. I would argue that this way is math. My pen is playing up again. This way that I just wrote down is mathy. I'm just using a math trick to solve the system, and the way above is a physics trick. So you're looking at different ways to do the same physics. Either one works though. Let's look at example 2. A farmer pulls their produce to market in 2 carts. The farmer pulls on cart number 1, which is 13 kilograms. So I'm going to go ahead and I'm going to draw that. I've got a force pulling on cart number 1 that's 13 kilograms. And cart number 2 is tied to cart number 1. Number 2 and is 45 kilograms. The coefficient of friction between cart 1 and the ground is 0.5, and the coefficient between cart 2 and the ground is 0.8. If the force of tension between the two carts is 457 newtons, with what force is the farmer pulling? So I think I've got all of the important details out of the question. If I don't know for sure yet, I would read it again, but I'm not going to put you guys through that. So what I'm going to do now is I'm going to take this quick sketch I did and turn it into a free body diagram. There would be my carts, and I can label them if I want. And again, I'm going to do my forces in red. My easy forces, I've got an applied force pulling on cart number 1. I've got an Fn going down on, or an Fg going down on cart 1. I've got an Fn going up on cart 1. I've got an Fg going down on cart 2 and an Fn going up on cart 2. And I'm going to go back and add those numeric subscripts. And now I need to think about some extra forces. It tells me that I have a force of friction, or coefficient, on both of these, which means on cart number 2, I'm going to have a force of friction on cart 2, and it also means I'm going to have a force of friction on cart 1. Notice how, again, if I take this and I cover these up, and I chose my wrong pen to do that with, if I cover these up, then box number 1 should be pulling, or sorry, box number 2 should be pulled forward. And I can see that right now nothing is pulling it forward, so I'm going to have to add a force to it. And since it's box number 1 that's pulling forward on box number 2, this is going to be my Ft, I will also have a force going back on box number 1. So those forces of friction add some complexity to this. Just adds a couple steps. So we have our 3 options again. We can look at, if we want, we can look at the sum of the forces on box 2 is equal to m2a, and this is of course in my x-plane. I could, if I wanted to, look at the sum of my forces on 1 in the x-plane is equal to m1a, and I could also look at, if I wanted to, look at the sum of my, whoa, that's the worst sigma symbol ever, the sum of my forces on the whole system is equal to the mass of my system times acceleration. These are my 3 options. You need to use appropriate subscripts so that both yourself and whoever comes after you to read your work can try to figure out what you're doing and what you're thinking. The object isn't to get to a right answer. The object is to prove that the answer you got to was right. Adding the subscripts helps with my proof and my process. So I have to decide which one of these 3 I'm going to start with. The question asks, with what force is the farmer pulling? So maybe I want to start with F1 or box 1 because that's what the applied force is. I have an FA minus FF1 minus FT is equal to M1A. And just because I haven't done it yet, I have called to the right and up positive. If I take a quick look at this, I will find that I don't know what FA is, and I also don't know what my acceleration is, I don't think, do I? So I'm a little bit stuck again. So I am going to choose to look at maybe F2, because it's usually a little bit simpler to look at than the whole system. So if I look at just box number 2, I've got a FT minus FF2 is equal to M2A. If I take a quick look at the things I know and things I could further expand, I think it gives me Ft in the question. Ft is equal to 457 newtons, and my mu2 is equal to 0.8. So I know what Ft is. I don't know what my force of friction on 2 is, but I think I might be able to calculate it. I know what m2 is, and I don't know what my acceleration is. So what I'm going to have to do is I'm going to have to see if I can expand this force of friction 2 out a little bit. Ft, I'm going to move it over to the other side first, is equal to m2a plus the force of friction on 2. And we'll notice at this step that our force of tension is required not only to accelerate that mass, but also overcome the force of friction, which logically makes sense. If I look at my formula sheet, my force of tension is equal to m2a. Force of friction is equal to mu Fn. I know what my force of tension is, so I'm actually not sure why I solved for that. I'm going to go back. I'm going to delete these. Sorry, my bad. And I'm going to go back here. I'm looking for my acceleration, which is then going to be equal to an Ft minus Ff2 divided by m2. That makes a bit more sense. I'm now solving for something I don't know. My acceleration is Fe from my formula sheet friction, normal force, m2. I also question if I look at some of my forces, and I can do this on the side, which is in a y plane equal to ma, that I'm going to end up in g. n is equal to 0, so f n is equal to g. Particular case, moving up down, find out with a, switch back to blue, is mu f divided by m2. And as you can see right here, I have already got that calculated. That's a little bit big. I plug numbers in appropriately. I should get the acceleration of this system is 2.31555 dot dot. So I can go back and I can look back at object number 1 again. I am looking for this applied force, which means I can substitute it in. I think I can figure out my force of friction on 1, know my force of tension, know my mass, now know my acceleration. I'm good to go. So if I rearrange this equation, my force is going to be equal to, there is some importance there, it's going to be equal to A plus F on 1 plus Ft. Force equal to which 13. Well, let's do that first. M1 plus my force friction, of course, is mu1, and it's going to go ME in T. There, now I know that A to be equal to M1 13 times my acceleration, just 2315 stuff, plus mu is 0.5. Notice how I'm writing A1 now because I'm anticipating not having to use that option for this question. My mass is 13, 9.8, plus my force of tension between the two is 151. And then I already calculated that guy too. Unfortunately, my pen is choosing times to quit today, and I'm not sure why. But I think I can read it if it's going to let me write. It's not even going to let me write. Ugh, I love it when technology works for me. There we go. Let's take this. That looks about. There we go. So my final answer would be, my applied force would be 487 newtons. I think I have just one more example. Example 3. 2 blocks of ice are being pulled along a field by a string. Block 1 is pulled by the string. Block 2, half the mass of block 1, is tied to block 1. If the action-reaction force between the two ice blocks is 834 newtons and the system accelerates at 5 meters per second squared, what force does the string apply to the system? So we're going to do the same thing. We're going to draw a little bit of a diagram first. 2 blocks of ice. For the record, you should look up ice blocking. It looks super fun. It's kind of like sledding, but in the summer. So this is 2 blocks of ice. Block 1 is pulled by the string. So this is block 1. This must be block 2. If the block 1, block 2, block 1, I don't have masses, 834 newtons, and my acceleration is equal to 5 meters per second squared. I don't think I have any extra information to pull from the question right now. I think those are the only things. This is exciting because I don't actually remember writing this question down, and I have no idea what to do. It's like going through completely fresh, so I'm going to do my free body diagram. I've got there, applied force, P1, I've got F1, and I'm doing my forces F2, Fn2, and then of course block number 2 will be block number 1 with the force of tension. If you're curious about these two forces of tension in the middle and how they work, what you should do is you get 2 of your friends, and you should hold their hands so that you're in the middle. I actually, instead of friends, maybe family members currently, people that you're living with, and have one of them try and pull you, and the other one to try and not move. And that's what should happen. And you should feel quite strong forces in each one of your arms. One of your arms will be being pulled by the person who's trying to pull you, and one of your other arm will be getting pulled, just trying to pull the person who's trying to stand still. Fun little fast experiment you can do with family members. So I think that's my free body diagram. And the question is, what force does this string apply to the system? So I'm looking for FA. I think this time, since I'm looking for FA, and I know what the acceleration is, and I'm getting pretty used to these options, I know that if I looked at 2, the sum of my forces on 2 is equal to ma. I don't know, now let's keep going. I call it my right positive. On 2, I would get, it'd be red, be consistent. F is going to be equal to M2A. I know my acceleration is. I don't know what Ft is, and it doesn't have Fa in it, so this isn't super useful. If I look at the sum of my forces on block 1 is equal to M1A, then my force minus the force of tension is equal to M1A. Sorry, I knew what Ft was on the red one. I don't know what M2 is. I don't know what M1 is, and I don't know what my applied force is, so I'm stuck a little bit here too, and I don't quite know what to do. So then I could look at, if I wanted my third option, the sum of all my forces on a system are going to be equal to the mass of my system times acceleration. And on my system, I have tension on block, tension on block 2 m2 times acceleration, and I will notice that F cancel, and I have A is equal to m1 2 acceleration. I don't know what my masses are again, and I don't know what my applied force is. So I'm actually quite stuck. I've tried my 3 normal ways, and I've looked at those. I haven't done anything wrong, so I've left them all where they are. But now I might have to use a little bit of critical thought. I think we're also given a relationship back up top here that might give us one more hint at what's going on. And I think it says block 2 is half the mass of block 1. So I can write that down as a mathematical expression. I've got an M2 and an M1. Block 2 is half the mass of block 1, so 2 times the mass of block 2 would be equal to the mass of block 1 if they're each the same. So right now I actually have 4 different equations, and what I'm going to have to do is I'm going to have to do a little bit of manipulation to try and figure out how to solve this system. So now we're going to have to rely on math skills. There's no ifs, ands, or buts about it. So what I could do in order to eliminate this, I might, the action-reaction force between the two blocks is 834 newtons. I know this. No, I'm making this harder than what I know. I know what F acceleration is. I don't know what M2 is, so I can use this red equation to solve M2. M2 is FTA. M2 would be equal to 834 newtons. I don't usually get this, so I won't. And my expressions. And let's see if I look down at the bottom. I actually did this. I've done this in the right order. That's why I'm ready. M2 is that. 160 kilograms. Cool. So now I have M2. So if I look at this equation, I don't know what the applied force is. I know what my force of tension is, my acceleration is. I don't know what M1 is. If I look at this equation, I can find out what M1 is because it's just 2 times M2. And instead of figuring it out numerically, I am just going to go ahead. Look at that. I did figure it out. I don't think I need though. I'm just going to go ahead and I'm going to substitute it minus M1 from 1 to 2 M2s times my acceleration. So my force is going to be equal to 2 M2 A Ft is equal to 2 times 8 times. So my applied one in this case is going to be 2,500 newtons, or to having some pen problems, 2,500 newtons, which would look like 6.5, 2.5, 3 much. And I think that was the last example.
Thank you for watching, and I just wanted to remind you guys a couple of keys for success. Number one, you got to do the practice questions. If the things I'm saying make sense, that's phenomenal, but you still have to practice and make some mistakes on your own. And that goes along with number two. If you get stuck, ask me questions, get in touch, write me an email, make an appointment, or leave a comment on the YouTube video